3 seconds before everything changes, the signal dies. Not a glitch, not interference, a complete, total blackout. 4 human beings hurtling toward Earth at 25,000 miles per hour, wrapped in plasma hot enough to melt steel, and the people responsible for bringing them home can do absolutely nothing. They just watch a blank screen and wait. And here's what nobody is saying out loud. When that signal comes back, it might tell us something about this heat shield that we are not prepared to hear. Quick question before we get into this. Where are you watching from right now? Drop it in the comments, because what I'm about to show you is something that should be in every headline today and somehow isn't. Stay with me until the very end of this video, because the moment I'm describing right now, the one that changes everything, I'm not going to explain it yet. You need the full picture first, and by the time we get there, you're going to understand exactly why the engineers are not sleeping tonight. Let's go back to the beginning. 4 astronauts, 1 capsule, 400,000 kilometers from home. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen just completed something no human being has done since 1972. They flew past the moon. And if you watched the coverage, you saw the celebrations, the press conferences, the stunning imagery. Historic, emotional, genuinely extraordinary. But here's what that coverage quietly skipped over. The flyby was never the dangerous part. Artemis 2 is not fundamentally a sightseeing mission. At its core, this entire flight exists to answer one question. Can we take this capsule with real human beings inside it through the full loop, launch, deep space transit, lunar flyby, and most critically, bring it home alive through an atmospheric re-entry that has never been attempted with a crew on board? Everything before the return was the prologue. The return is the actual story. And the return has a problem. Actually, it has 3 of them, and they are all happening at the same time. Problem 1, the heat shield. After the first Artemis test flight, the one with no crew, engineers brought the capsule back and looked at the heat shield up close. What they found did not match their predictions. The material had charred unevenly. Certain zones had eroded deeper than the models said they would. The pattern of heat damage was asymmetric in ways their simulations hadn't captured. Now, to be precise, the capsule was never in danger of breaching. The margins held, but the models were wrong. Not catastrophically wrong, but measurably, documentably wrong. So the engineers did what engineers do. They updated the models. They ran new analyses. They cleared the mission. But here is the thing that should make you pause. A model that explains data it has already seen is very different from a model that accurately predicts data it hasn't seen yet. The updated model fits the first flight. What it cannot guarantee is that it fully covers this flight, because this flight is not the same as the first one. This flight has a crew, and a crew changes the thermal signature of the vehicle. The mass is distributed differently. The heat absorption profile shifts. And on top of all of that, this capsule has spent the last 72 hours soaking in something that the first test flight never had to deal with. Problem 2, the sun. Solar Cycle 25, the current activity cycle, has been running hotter than forecasters predicted. Over the past 3 days, the Artemis 2 crew has been transiting through a sustained elevated particle radiation environment. High-energy electron flux readings significantly above baseline, geomagnetic disturbance activity during the early transit. And right now, as the capsule approaches Earth, there is an active sunspot region with a 10% probability of firing an X-class solar flare, the most powerful category, while it is still pointed directly at the inner solar system. 10% sounds small, but in aerospace risk management, when you are talking about 4 human lives in an unrecoverable situation with no abort options, 10% is not a number you dismiss. It is a number you build contingency plans around. But the X-class flare risk is actually the more dramatic and less technically sneaky of the 2 solar concerns. The quieter one, the one that very few people are talking about, is something called dielectric charging. Here's how it works.
high-energy electrons penetrate the outer skin of the spacecraft and bury themselves inside the insulating materials beneath: plastics, composites, wire coatings, circuit board housings. Because those materials don't conduct electricity, the electrons don't dissipate, they accumulate. They build up a static charge locked inside the structure. And when that charge releases, which it will, unpredictably, at a moment nobody can schedule, it produces a spike, a burst of electrical noise that can look like a sensor reading slightly off, a data packet arriving corrupted, a guidance input registering a fraction of a degree different than it should. None of those effects individually constitutes an emergency, but 72 hours of sustained exposure doesn't produce one spike. It produces the conditions for many small, distributed, unpredictable disturbances across a vehicle whose most critical flight phase requires precise, real-time autonomous guidance corrections made faster than any human can respond. Which brings us to problem 3.
The return maneuver for Orion is not the same kind of re-entry the Apollo astronauts used. Apollo capsules came in steep, a single ballistic plunge, brutal deceleration, up to 8 times the force of gravity pressing the crew into their seats. But physically, it was relatively predictable. One heating event, one trajectory. The thermal protection system had one job. Orion performs what engineers call a skip re-entry. The capsule dips into the upper atmosphere at a shallow angle, generates aerodynamic lift, yes, actual lift, the same force that keeps aircraft flying, uses that lift to bounce back out of the atmosphere, and then comes back in for the final descent. 2 atmospheric interactions, 2 heating peaks, 2 complete thermal stress events on every seal, every material, and every sensor on the vehicle. NASA chose skip re-entry for good reasons. It reduces peak G-forces on the crew. It allows more precise landing zone targeting. These are real benefits. But the engineering trade-off is profound. During a skip re-entry, the vehicle is flying itself. The guidance computers are making dozens of real-time corrections every single second through an aerodynamic environment that is changing faster than any human pilot could process. And here is the coupling that matters. The output of the first atmospheric pass directly determines the starting conditions for the second one. The angle of entry sets the depth of atmospheric penetration. The depth of penetration determines dynamic pressure. Dynamic pressure determines heat load on the shield. Heat load determines how the ablative material chars and erodes. The way it erodes changes the surface geometry of the capsule. The changed geometry affects the aerodynamic forces, and those aerodynamic forces are what the guidance system is using as its reference to calculate corrections for the second entry. It is not a sequence of independent steps, it is a feedback loop. And the feedback loop runs directly through the exact component whose real-world behavior did not match predictions on a last flight. Now, stack that on top of 72 hours of dielectric charging in the avionics. These sensors feeding data into that guidance system, the same sensors that have been accumulating unpredictable electrical noise for 3 days. The corrections the computer makes are only as accurate as the inputs it receives, and the inputs have been in a charged particle bath since shortly after launch. Each of these risks, the heat shield model divergence, the electron flux exposure, and the guidance dependency of skip reentry, cleared its own certification review. Each was individually assessed and approved, but the combination, this exact combination on a crewed vehicle in this specific solar environment at the end of this specific transit profile has never been tested simultaneously, because it couldn't be. You cannot test this combination without flying it. Artemis 2 is the test. That is what a first crewed qualification flight actually means, even when no press release says it quite that directly.
Now we are back to where we started. The signal is dead. The telemetry screen is flat. The capsule is somewhere above the Pacific, invisible behind a sheath of ionized plasma heated to temperatures that rival the surface of the sun. And everyone at Mission Control is doing the only thing they can do: waiting. This phase is called plasma blackout. It lasts 3 to 5 minutes during the first atmospheric interaction of a skip reentry. 3 to 5 minutes during which the guidance computers are navigating the most demanding flight sequence of the mission. The heat shield is experiencing its first thermal peak. The avionics are operating on sensor data shaped by 3 days of charged particle exposure. And the AV coat material is either behaving the way the updated models predict or producing another result that nobody fully anticipated. And no command can be sent. No data comes back. If something diverges from the nominal profile in those minutes, the spacecraft handles it alone. Or doesn't. This is the moment where the individually acceptable risks are all present simultaneously. The model divergence that wasn't fully explained after the first flight, the electron flux environment that nobody can fully characterize until the post-flight data comes back, the feedback loop of a skip re-entry running through systems that have been stressed in ways that simulation couldn't perfectly replicate. All of it arriving at the same moment in the most thermally extreme environment the vehicle will ever encounter. The blackout ends, telemetry returns, and in the hours and days after splashdown, engineers will pull apart the data. The thermal scans of the heat shield surface, the recorded guidance trace, the navigation logs, the sensor histories. They will compare what happened to what the models predicted, and they will measure the gap. And that gap, whatever size it is, becomes the foundation that Artemis 3 is built on, the mission that will actually land people on the moon. The real stakes of this re-entry were never just about these 4 crew members, as important as they are. The stakes are about what we learn, about how honest we are willing to be about what the models said versus what reality delivered, about whether the gap between prediction and outcome is small enough to build a future on. There is a phrase that circulates quietly in aerospace engineering circles after a flight that confirms something the models got wrong. It goes like this: the system worked, but not entirely for reasons we fully understand. That phrase appeared after Artemis 1. And right now, somewhere above the Pacific Ocean, we are in the process of finding out whether it appears again. The parachutes open, or they don't. The shield held, or it surprised everyone again. And either way, humanity will have learned something that cannot be learned any other way, by sending real people into the unknown and watching what comes back. That is what it means to be a species that has decided to leave this planet. You reduce uncertainty until it feels manageable, and then you fly. If this gave you something to think about, share it with someone who still believes the flyby was the hard part. And subscribe, because whatever those post-flight engineering reviews reveal, this channel will be here to tell you exactly what it means. The story is not finished yet.